we're just going to act normal, right? Please talk. He wants to hear your voices. All right. Anyways. All right, so we're going to talk a little bit about related rates. Here's the thing. Related rates it's a pretty big deal, but it really comes from stuff we've already talked about. If you remember, implicit differentiation is when we were taking the derivative with respect to a variable, and we were taking the derivative of some other variable, like the derivative with respect to x of y would be dy over dx. Sometimes when we took the derivative, we had to apply the chain rule. Because in this case right here, y is inside of a function squared. We're taking the derivative with respect to x of y squared. Because the variables don't match up, what we did is we took the derivative of the outside, we left the inside the same. So if this was an x, then it would be normal. We would have gotten 2x. But because the variables don't agree, we're then applying our chain rule and taking the derivative of the inside. So we took the derivative of the outside, we left the inside the same, and we multiplied by the derivative of the inside. Of course, the inside is y, and we're taking the derivative with respect to x, and that's where we get our dy over dx. So, implicit differentiation is going to play a part in related rates. Basically, we're applying this idea right here. If you're thinking the whole time like, man, implicit differentiation was pretty dumb or something like that, well, here we're going to see some really practical uses of implicit differentiation. All right, let's take a look at this. Says that variables x and y are differentiable functions of t. Okay, so all that's saying right there, if that is some scary words, it's saying that x and y, we can take the derivative of them with respect to t. They're saying that those derivatives exist. That's all they're saying right there. So basically, all they're saying is, hey, look, you're not going to get any errors. Don't be concerned. And they tell us we're relating. We can relate those variables with this equation. We have an equation that relates x and y. None of this is unusual, right? We can typically take the derivative of x and y. We oftentimes have x and y related in a function. There's nothing crazy about this. But then they give us some information that is a little unusual. They say, find the derivative of y with respect to t. That's our goal for this problem. When x equals 1, so I'm going to write that down as at x equals 1, because, super cool millennial. And it's given also that dx over dt is 2 at that same x value of 1. So when we're doing these problems, the related rate problem, they're going to stick out. It's going to be pretty obvious most of the time. They give you a lot of information. And the first thing that I would always encourage you to do is just start writing it down. Here, they gave us that information in the notation that we would be used to, but they might say things in words, and we're going to want to convert it to the notation that we're used to. That's going to make it all a lot easier on us. And hopefully, as we look at these things, what has stuck out and what has been the weirdest thing of all is that our derivatives are with respect to t. I would think that's probably the weirdest part of all of this, is we have derivatives with respect to t. And in mathematics and in science, when we're trying to apply this stuff, a derivative with respect to t is saying a derivative with respect to time. We are going to be relating a lot of variables with respect to time. And we're essentially saying, how is x changing as time changes? Like when you drive a car, miles per hour is your speed. Well, that would be a change in distance over a change in time. So your instantaneous speed of your car would be the derivative of the distance with respect to time. So this is just essentially, when you see the dt, that is the variable in which we're relating these things through, and it's essentially saying, hey, look, this can be a real scenario here. We're relating them with respect to time. And that also means if I have these things, it's a dead giveaway. We're going to use our equation, and we are going to take a derivative of this thing with respect to time. If we have stuff to find and we have stuff to use that is dt, then I need to take the derivative with respect to t so I get that stuff. And that is usually, if not 100% of the time, when we're dealing with these related rates problems, we're going to have to take the derivative with respect to t at some point. When I do that, we're going to apply it to everything, right? We're taking the derivative with respect to t of this whole equation. On the left side, I get dy over dt. The variables didn't agree. Y is just y, so I'm taking the derivative of y with respect to t. Boom, there it is. I've dealt with the left side. The right side, x squared, well, the variables don't agree. It's squared, so I'm going to have to apply the chain rule. I'm going to take the derivative of the outside. I'm going to leave the inside the same. But then I'm going to multiply by the derivative of the inside with respect to t. Again, notice for the outside, leaving the inside the same. And then I multiply by the derivative of the inside. Even though it's x, I'm not taking the derivative with respect to x. Finally, the derivative of a constant, doesn't matter what variable, the derivative of a constant is 0, so that is gone. Now, we've done all the hard stuff. We want to find dy over dt. We already know that x is 1. We already know that dx over dt is 2. And so dy over dt is 4. That's what we were looking for. We were looking for the change in y with respect to time at the moment where x is 1 and the change of x with respect to time was 2. We wanted to know, what was y doing? How was y changing at this moment where x is 1 and dx over dt is 2? This was a specific moment, and we were finding what dy over dt was doing, while this other stuff was doing these other things. Thoughts about that? Related rates? All right. Yeah. Let's take a look at this first one right here. Take a look at this first one. So instead of writing it all out as a sentence, you're looking for dy over dt, just like we did a second ago, when x is 3 and dx over dt is 2. So taking the information, they've already kind of written it out in that notation we would expect. Let's try to find dy over dt. So you can see here, really the big crucial step is knowing that since we have derivatives with respect to t, we're going to take the derivative with respect to t of both sides of our equation, where we've related the x and the y. And if we do that correctly, we'd be careful with that implicit differentiation. We then plug in what we have to find what we're looking for. That's really it. Any thoughts, questions, concerns about this? Luis? All right, we got about 5 minutes. I want to take a look at a real problem that's really related, a real situation right here. So here we go, 5 minutes. All right, so here's our situation. We got a pond, right? It's a nice calm pond, and we drop a pebble in the pond. All right, we can all imagine this situation. You know, if you've never been to a pond, imagine a bathtub. What? All right. When we drop a pebble into a pond, it starts forming ripples, and ripples are expanding out of that place where we dropped our pebble. So again, imagine that. It almost has a sound effect to it. And they form concentric circles. If you don't remember, that just means that all those circles have the same center they're all expanding out of that place where we dropped our pebble. It says the radius of the outer ripple is increasing at a constant rate of 1 foot per second. The outer ripple, is increasing at a constant rate of 1 foot per second. So notice that it's changing per second. That is telling me that the radius is changing with respect to time at 1 foot per second. So again, there is how they can give us words, and we're going to want to translate it into notation. Clearly, reading this and using this is going to be easier than trying to keep up with those words. So I would write it down. It says when the radius is 4 feet, so that's how I write it down, at r equals 4 feet, at that moment, because notice the radius is increasing at this constant rate, 1 foot per second, but there's a moment where the radius is 2 feet, there's a moment when the radius is 3 feet, and there's a moment when the radius is 4 feet. That's the moment we're looking at. At that moment, at what rate is the area of the water that has been changed? At that moment, we are looking for the rate of change of the area. That's our goal. So again, when there's only 1 foot radius, there's a small area. But we're looking at this moment when there's a 4 foot. And we could find the area right there, but we want to know at what rate is that area changing. We want to know clearly it would just be 16 pi would be the actual area. We want to know the rate at which that area is changing. That's our situation. Once we write down all the given information, we do need an equation that relates these variables. We're talking about circles, we're talking about the area, we're talking about the radius. The area of a circle is pi r squared. I hope we remember the area of a circle formula. If not, there it is. That is an equation that they could expect you to know on the AP exam. We will certainly use it a lot between now and then. And we're going to now once we've got all this information, we do exactly what we've been doing. Because I have derivatives with respect to t, I'm going to take the derivative with respect to t of both sides. Over here, pi is just a constant, so don't be scared of pi. Over here, we get 2 pi r times dr over dt. I took the derivative of r squared and then multiplied by the derivative of the inside. Again, pi is a constant, so it's just hanging out. Plug in what you have to find what you want. dA over dt is going to be 2 times pi times 4 times 1, and we get 8 pi feet squared per second. That's it. We solved it right in the nick of time, but hopefully that kind of I wanted to give you some context as to why and how all this stuff matters. So at that moment, the area is increasing by 8 pi feet squared per second. We'll talk more about it tomorrow for sure. Let me know if you have any questions. And after we look at a little bit of related rates at the beginning of class, the rest of the class is working on review problems, asking questions, and we'll do that on Thursday as well. So please come with questions if you have them.